12.2 Vector Basics, and this is really part one. If we have a point P0 located in space and a point P1 located in space, if we draw a line segment from P0 to P1 with an arrow on it indicating direction, that denotes a vector. A vector sometimes is called a directed line segment. And you can indicate P0, P1 with an arrow over it. And we can specify the vector as simply delta x is x1 minus x0, delta y is y1 minus y0, indicating those changes denotes the vector. You can simply say x changes by 5, y changes by -2, and you've described a vector. It's that simple. Now, instead of saying x changes by, we use these pointy brackets in calculus. This notation tends not to be used in physics, but we feel special because we've reserved it for calculus. If we have a z-coordinate, I kept it in 2 dimensions for simplicity's sake. If we have a z-coordinate, it's just comma z1 minus z0 and pointy bracket. Now you can also say the same thing, x1 minus x0, I with a hat over it, y1 minus y0, j with a hat over it. I with a hat over it simply means delta x equals 1. So if you multiply, if this is 5, 5 times delta x equals 1 means delta x is 5. J hat means delta y is 1, and k hat, that's a sloppy k, but that's a k hat means delta z is equal to 1. So that's all notation. Now, we have a whole vector algebra, vector addition. If you take a vector 2, 3, 1, add it to 3, 1, 4. 2 and 3 is 5, 1 and 1 is 2, 3 and 4 is 7. All we're saying is we have a delta x of 2, then a delta x of 3. Altogether, x changes by 5. It's very simple. Here's the rule. Quite often we parameterize a vector u and a vector v by just saying ux, uy, uz, vx, vy, vz. And we can state the rule, you add 2 vectors by adding x, adding y, adding z, that's all. Scalar multiplication, 2 times this vector. We have delta x equals 3 2 times, we have a delta x of 6. Delta y is 5 2 times, we have a delta y of 10. Same thing for z, 2 times 4 is 8. You just multiply this number through. Very simple. Here's a rule, k on the outside, we just put a k by each of the components, multiply it if they are numbers. Now, magnitude, length, or norm, you'll see all these terms floating around. If we're talking about pure coordinate geometry, we'll probably use the term length because we can sketch a vector and either use coordinate geometry to figure the length, or we can take out our ruler and measure the length that would give us the same answer. Magnitude is generally a physics term, so if we have a force vector, for instance, all this vector algebra can be used to specify force, for instance. We generally don't say a force has a length, but it has a magnitude or a strength. And then norm tends to be a linear algebra term. And we generalize that because in linear algebra we talk about higher dimensional vector spaces, 4, 5, 6, and 7. And so if we're operating in 7 dimensions, length ceases to have meaning. We can't measure anything in 7 dimensions. So you can use the term norm freely in 2 and 3 dimensions, and then it will continue to be used in linear algebra. Well, in any event, the norm of 2, 3, 5, which is the length if you sketch this in 3 dimensions. It's a 3-dimensional Pythagorean theorem, square root of 2 squared, 3 squared, 5 squared, square root of 38. 25 and 9 is 34, and 4 is 38, which is going to be 6 point something, low 6s. Okay, those are some basic definitions. We'll be back with part 2, which will just work some problems to give you some insight into how to complete your problem set.